screen, the first slide.
Yes, sir.
Yes, sir.
So as we had promised in the previous class, we will talk about two remaining topics. One was the structural design for fire, and the other one is the base plate design, which is part of mostly a part of compression members. Splices could also be covered, but splices are not only in columns. Splices are provided in beams also. So I would rather have that covered by Professor Madhavan if he wants to, but I will definitely focus on these two parts. Then one is fire design, because I already work in that area, so it's much easier for me to cover it. Then there is another topic which we should usually cover is the fatigue design, right? But I don't think we will have time to cover that fully. But see if Professor Madhavan has some time towards the end to cover that topic. You can discuss with him if you're interested. So here is a video. I don't know, some of you might have attended, those who are who have been at IIT before, some of my sessions. So you might have seen this video. So in this video, this experiment was done by, can you see the entire screen? Can you see the very bottom of this screen? It says Underwriters Laboratory, right? UL. Can you see UL sign under it? It's kind of the corner, at the very corner, it is kind of getting cropped. So that is basically Underwriters Laboratory. They are one of the, here also it mentions at the top left. These are one of the major agencies. It's a private agency which does a lot of research on structural fire resistance or in general fire safety. Okay. So they are kind of in between the fire protection communities and the insurance companies, right? So they have a very important position too in that way. So they simulated, but when I say simulated, it's not a computer simulation, it is a real simulation. It's more realistic. So they basically built two artificial chambers, compartments, right? Like a room. They created two rooms. They had, both these rooms had a lot of, like the entire front door was open. This kind of an opening was there. One room was a more legacy kind of a room. So this was a typical drawing room, maybe in the US from the 70s and 80s, right? So the furniture in this room was entirely made of wood. The upholstery, the curtains, the cushion, everything is made of cotton, right? So it's more of a natural organic materials that are used in this. So the table furniture there, that is all real wood, right? Not the synthetic kind of this dry, what is it called? The particle board kind of a wood. This is a more modern drawing room wherein the furniture is made of this lightweight wood, which is not really, it has some part wood, but it has a lot of organic synthetic adhesives and those kind of things. So for example, particle board. Have you guys seen particle board ever? What is a particle board? What am I talking about? Particle wood board or particle board or wood particle board. Anybody knows what it is? At least plywood you would know, right? All of you would know plywood.
Yes, sir.
Right? So, yeah, so plywood has more wood content. Basically, what you have is different veneers of wood. So you take a big log of wood, you cut like 1 millimeter thin or 1.5 millimeter thin layers from a big wood log. Okay. And then what you do is you put those layers, one in this direction, the other one in this direction, then the other one again in this direction, in this direction. Likewise, you keep stacking them, and in between you put some adhesive, which is mostly some kind of an artificial, some kind of a synthetic adhesive, and then you bind them together. Okay. Why it is better than proper natural wood is because you can manage with small pieces of this wood, and you can cut. Like, you can just join them together. So that's how plywood is made. So plywood does not have to have a continuous piece of wood. Typically, plywood comes in the shapes of 4 feet by 8 feet, in the sizes of 4 feet by 8 feet. Okay. Particle board is even worse quality product. It is basically almost like a sawdust. So sawdust would have different sizes. When a big log of wood is cut using a chainsaw or something, you will have sawdust coming out of it, right? That sawdust will have different size particles. So you may have a very small size particles. Even they are often collected together, compacted, and then infused with some kind of a resin, which is basically an adhesive, and bound together. So that is also one type of a particle board. Then you have slightly larger size particle boards. where the particle size is slightly larger. So you have variety of them, and then how tightly you compact them, how tightly you pack the wood in that system, that controls the quality of that artificial wood or manufactured wood. Okay, and most of the modern furniture is actually made of one of these woods. So if you buy a, like, you go to any local furniture shop, cheap furniture shop, and you want to buy a table, a study table, right, your desk, and let's say you get a desk for 1,500 rupees or 1,000 rupees. I can bet my last dollar, that it will be a particle board kind of material. It will not be a, so particle board is nothing but your cardboard, right? Almost like a cardboard. Okay. So that is the kind of material the furniture is made of. And most of the upholstery, which is basically your curtains, your cushion covers, and all those things, and cushions, they are all made of nylon or other types of polyester or nylon or those kind of materials. So they ignite fires in these two compartments. And basically there is a phenomenon called flashover, which is basically the time when the entire compartment, if a compartment is in fire, the moment when the entire compartment catches fire, that is called flashover. It is not really a fixed second or a fraction of a second. It's not an instant, but you can very clearly see that there is a very clear demarcation, maybe spread over 2 or 3 seconds, before which the fire was more local, and after which the fire suddenly becomes engulfs the entire compartment. So they are comparing the behavior of this kind of a legacy compartment with a modern compartment, modern room. Okay. So you watch this video. So these are the two compartments. What they did was they lit a fire in a corner in both compartments. So here there was a small candle they had put, and they had put some kind of a shawl or something which catches fire. Here also they had put a candle which and then a shawl or some kind of a drape catches fire. And you can see that since this one on the right hand side is made of more of a synthetic material, the fire is growing much more rapidly than a typical woolen or a cotton kind of a material, which burns much slowly. It is much denser material and burns much slowly. So you can see the fire is growing much more rapidly on the right hand side. The amount of black smoke you can see that is coming out of this compartment. If this door was not open, this compartment would have started accumulating a lot of this smoke, and the people inside the compartment would have found it very difficult to survive. So by the way, the one thing you should notice is that the time is scaled up. So we have already done 3 minutes of fire. So within 3 minutes, you can see the fire on the left-hand side, which is a legacy room, was still very small fire. You had plenty of opportunity in the first 5 minutes to control this fire, so you can come with a fire extinguisher and douse this fire but much more easily. But in a modern compartment, within 3 or 4 minutes, probably they went a little bit overboard, and they might have used all the material which is much more combustible. But philosophy does not change. The basic trend does not change. So you can see that the fire has grown to the size in this compartment now that's almost a flashover right now on the right hand side. Whereas on the left hand side, the fire is still relatively a local fire. So they are calling at 3:40, it had turned into a flashover when everything in the compartment was burning at the same time. Whereas this one is still not a flashover fire. It is still slowly growing. It has burned the entire, So what is happening is, since this one is so bright, in the same camera, they are trying to capture this picture. So therefore, this picture is not bright enough. But anyway. So now you can see that the fire it took about 29 minutes for the other compartment to get to flashover, right? So that is why the fire nowadays in a typical building becomes a much bigger concern than it was, say, 20, 30 years ago, right? Because we are using much more combustible materials in our houses, and as India is also growing in economic prosperity, our houses have more material which can burn, right? So in a typical countryside household, let's say you go to a village somewhere, you don't have a lot of combustible material. You may have a roof which is thatched roof that may catch fire, but nowadays even that one doesn't. Thatched roofs are also very uncommon. You typically have a regular brick walls and concrete slab. That is a typical even in villages, that is a typical house. But the number of curtains they have, or the thickness of the curtains, or the material the curtains are made of, similarly the bedding, all those material, which is typically much more stiffer, much more denser material, that doesn't catch fire very quickly. Or even if it does catch fire, it does not spread fire that fast. Whereas the more modern materials, which are all these, the material with which our matrices are made of, right? So this foam, different types of foams that are used, memory foam and this foam and that foam, and all the ply that is used in the construction, and all the plastics that is used in our construction nowadays, our windows, sometimes even the window glasses, window frames, they are all made of plastics often. And our curtains are hardly ever cotton anymore. They are all different types of polyesters. So they catch fire much faster. These are all hydrocarbons which catch fire very fast. So there is something called flashover, when we can say is that even though all the fires start locally, right? So you may have a candle toppling in a compartment, or you may have some kind of a electric short circuiting, or a cigarette which you forgot to completely douse. And those things can light a fire, but slowly that fire spreads, and there is an instant when everything is inside the compartment starts to burn. And there are some kind of a quantification also. So when we have this kind of a radiation generated in the compartment, then you can call that transition as flashover. Okay, so for flashover to take place, it is very important then that the radiation that is generated by the fire is confined in the compartment. If there is no compartment, for example, if I have a barbecue, so if I take some coal and burn it out in the air, I will never reach the flashover kind of a situation, right? The intensity of fire will never reach that level, because the radiation that is generated from that coal has a way to escape. The radiation does not, all that heat does not keep bouncing back from different walls. In a compartment, however, whatever radiation you are generating, it keeps bouncing back from one wall to other, and it stays inside the compartment for a very long time. And at a particular point, that radiation becomes so intense that it starts burning things which are far away from the real flame. So I may have a flame in this corner, and this is creating a lot of radiation, and that radiation is accumulating near the roof of this thing in the form of hot gases, okay? And they are radiating heat back to everything. So let's say one compartment, one corner has fire, a plume of fire is rising from here, okay? One flame is rising from here, and with that flame, we have got a lot of smoke accumulated near the ceiling, and that smoke is radiating heat downward on everything. And there may be a table sitting far away from this flame, but that table can also catch fire because of the radiation that is falling that is hitting it from the ceiling, and that is called flashover fire. So typically, a real fire looks somewhat like this. So if you take a compartment, you measure the temperatures, the fire remains local for a very long time, or for a reasonable amount of time, which is called ignition phase, and then smoldering phase, and growth phase, up to certain point. And then at some point, it turns into a global fire. Okay, and in real cases, in any real fire, this transition from local to global, or the pre-flashover to post-flashover, is not very clearly demarkable. You can call it here, you can call it here, you can call it here, whatever. Then what we do is, in structural fire engineering, we don't really always generate fires like these. Okay? These are more realistic kind of fire, but we need a standardized way of fire time temperature plot. So we generate furnace. We have to generate fires in furnaces. So you create a furnace. Within that, we put the structural member, and we want to test its behavior at high temperatures. So that furnace is usually standard fire curve. So this is how a standard fire curve looks like, this yellow line. Okay. So basically, it is somewhat of a curve fit of the global phase of the fire. So when the fire turns global, and then most of the real fires start to die out after some time. So why do they start to die out after some time? Why does the fire die out? A real fire.
Once the material is over, there is no more material.
Yes. So everything that is, yeah. Go ahead. Okay, I'll carry on. So yeah, so everything that could burn, everything combustible that was fuel for the fire, once it gets over, once it gets consumed, then the fire starts to die out. But in a real, but in a standard fire that we use for our experiments, we don't have that dying out phase typically. We keep the fire going for longer and longer, because the idea is that we are trying to simulate different types of compartments within a single test. So if we test this, if we conduct a test for 1 hour, so basically here in a furnace, the fuel is not stored inside the furnace. Fuel is pumped into the furnace as the fire grows. So the fuel could be your CNG or mostly LPG rather than CNG, or LNG, liquid natural gas, or it could be kerosene, or it could be some kind of a other petroleum that is generally pumped into the furnace while the fire is going on. So so there is no reason why the fire should die out, because you can always keep pumping the fuel. Also, sometimes you have to mix some oxygen with that, because the compartment does not have the furnace does not have a natural access to oxygen, whereas the real compartment has some windows and doors from where it can get natural oxygen, like natural air through convection. So this is how a standard fire looks like. So basically what we try to do is, this is the flashover point. So basically what we say is that we are shifting that point a little bit sooner, and we are saying this is the flashover point. So as soon as the fire hits, the fire intensity is so huge that immediately it engulfs the entire compartment, but the compartment is at a low temperature in the beginning. So it takes some time for the compartment air to reach that kind of a temperature. But anyway, it grows. So initial growth is very rapid, and slowly the temperature rise slows down. And at around 1200 degrees centigrade, we just maintain that temperature. We don't keep going higher and higher. Okay. So that's how the typical structural fire testing is done. Now, I was talking about the density of the material, right? So whatever, let's say you talk about wood. So now how dense the wooden artifact is. So you may have a very heavy, dense wooden door, or you may have a very flimsy wooden door, which is like a 1.5 or 1 inch thick wooden door. Which one will catch fire quickly or more easily? Which one do you think will catch fire more easily? Something that is like, 6 inches thick, heavy wooden door, like a fort door. In the older times, these forts used to have very heavy doors, right? That kind of a wooden structure, or something which is much thinner.
Thinner, sir.
Thinner one, right? Yeah. So the reason is there is some kind of a parameter. There is an entire science for combustibility of materials. And of course, what matters is that how much oxygen is available for the surface. So oxygen is available only at the surface, but material is there inside, packed inside. So if you have more surface available, then that means you also have more oxygen available, right? So that makes it easy to combust for any material to burn. Do you think steel burns? I mean, we have never seen steel burning. So here is a video for you. If you take a steel beam and you light it out, if you take a steel beam and you try to you take a gas torch and put it in front of a steel beam, it will not catch fire, right? But if you distribute that mass over a large volume, then you can see what happens. Can you hear his audio? What he's talking, can you hear him?
No, sir.
No, sir.
Also,
Let me switch on the captions. I don't know how to do that. I have never been able to. When my son takes his classes, his teachers are able to do that. I have never figured that out. How to communicate this audio of the mobile, of the laptop. Okay, so basically, even steel can burn, right? So, but that doesn't happen often in our real life structures. But it is important to understand that when steel is basically an extreme example. But when you are dealing with fire, any material that is well compacted will not catch fire easily, or will not be. Okay, so see, basically, burning is what? Burning is just oxidation, right? So, and almost everything can oxidize, like steel does oxidize, right? We know iron of steel, that iron that is present in steel oxidizes. We all have learned those equations, chemical reactions. But what is burning? Burning is basically of course, oxidation is required, but through that oxidation, we should be able to generate enough heat so that that burning reaction is sustainable. That is the important part. So we should be able to generate enough heat, plus we should have enough oxygen available to maintain that oxidation reaction. So burning is nothing but oxidation, but it has to be self-sustained. If it is not self-sustained, then it is not burning. Something that is not, so something for something to be combustible or something to burn, the oxidation reaction should be self-sustained. So wood typically is able to sustain the burning process because it generates enough heat so that even a very well compacted, a big log of wood can burn. It will burn slowly, but it can burn. A big piece of steel will not burn because it does not produce enough heat through its oxidation so that it can even keep oxidizing the internal layers. But if you fluff it out like that, then you will have enough oxygen and enough heat density available, which will keep the burning reaction going. But that is more of a theoretical subject of study. It's not relevant for structural engineers. We typically deal with big sections of steel, which will not catch fire on their own. But when we talk about something catching fire, we should keep in mind that it is the density, how tightly it is packed, that material is packed, that also plays a role. So what happens to steel? Of course, burning is an extreme case. That won't happen to our steel that we deal with. But what does happen to steel? Two primary things happen to steel. One is, these are, can you quickly see what are these? So the first curve here, that is at 20 degrees centigrade. This is temperatures, 20, 200, 300, and so on. So at 20 degrees centigrade, your stress strain plot looks like this. And I have normalized the stress strain plot so that your yield stress is called 1. So let's say the yield stress is 1 at ambient temperature. So the stress strain plot looks like this. I have not plotted the strain hardening portion. So I'm going only up to 0.03 strain. There is no strain hardening yet. Now, at about 0.002 or 0.0015, somewhere around, it yields, that is this location, and then it maintains that stress level. As the temperature increases, so 200, 300, 400, let's look at 500. At 500, even though you cannot see it very clearly, the elastic modulus has reduced quite a bit. At 600, in fact, it has reduced very significantly. Right? So elastic modulus changes quite significantly. What does that mean? That means that steel becomes more flexible. Right? For the same amount of force, if I apply this much of force, let's say, then steel will deform much more than it did at ambient temperature. Also, what happens to steel is that its Fy changes. Its Fy, which was 1 before, has changed to almost 0.4 or 0.45 or something like that. Okay, so this is just a representative. In real life, you will see there are different types of steels and they all behave very differently or somewhat differently. Also, it depends on how you are testing it. There are various protocols for testing. That also changes the behavior quite a bit. This is just one example which is taken from the Eurocode, okay, which is a good representative of the overall behavior. Fine. What else happens? Elastic modulus changes, yield stress changes. Another thing that you might have noticed already, the first thing that you might have noticed, in fact, is that the behavior at ambient temperature was bilinear or almost bilinear. We know that, right? So there is a very clear, distinct yield point. You go up to a particular stress, up to that stress, it is elastic, perfectly elastic, and beyond that point, it becomes plastic, right? So you have a very clear, distinct yield point. At high temperatures, even at 200 degrees centigrade, that feature goes away. So now you have a more of a curvy linear behavior. You can see there is no clear demarcation of deviation from the yield point, from the linear elastic behavior. So for some initial stress level, it remains elastic almost, but it's not very clear, very easy to identify at what point it becomes non-linear and deviates away from that point. And slowly you have that strain hardening behavior at high temperatures, even though at ambient temperatures you didn't have strain hardening here. Okay, so these are the three things that happen. One is that proportionality limit. At ambient temperature, proportionality limit and your yield stress are the same, but at elevated temperatures they are different. This is your yield stress, and proportionality limit is somewhere here, much lower. Second thing, elastic modulus changes, reduces. Your yield stress reduces. Okay, what else happens? Another thing is that creep starts to play a very significant role at high temperatures. We will not discuss that one too much here. This is something that happens to concrete. So this course is not about steel, so I'll not focus too much on that. Typically, the reduction in strength of steel and concrete goes somewhat like this with increasing temperature. So this is your steel yield stress. Up to 400, your yield stress remains almost about the same without much of a change. But even though the yield stress remains the same, elastic modulus decreases quite a bit. So the tension members may not change, their strength may not change very much, but compression members' strength will change quite significantly. And concrete also, up to 300-400 degrees centigrade, concrete performs more poorly than steel. But after that, the performances are almost similar, right? Different types of steels also. The steels that are used for different purposes, they have a slightly different performance. Basically, your structural steel, which is your hot rolled steel sections, they have slightly better performance than your weld steel or bolt steel. Okay. So at high temperatures, you can see concrete. Typically, what happens to concrete? You can see it undergoes a lot of cracking, like what you can see here. Can you see the cracks in concrete member? This is a concrete column, square column, okay, that we had heated in our lab. And you can see the discoloration of concrete, right? So concrete generally was originally of this dark gray color because it was a relatively new specimen. The part that was heated to almost 1000 degrees centigrade, its color changes to almost like this pink orangish color, right? And that is basically the aggregate, the granite aggregate, which is gray in color. That itself also changes the color to more of a pink orangish color. Steel, typically after fire, this is a picture from a real building. This was a column that was heated to very high temperatures, and you can see how it has deformed right next to the beam. So these are the 4 beams that are meeting this column at this location, and you can see how the deformed shape of the column looks like. So this is a squash kind of a failure. Okay. To concrete, there is something called explosive spalling. I'm not going to spend time explaining that. There is something else that happens to steel and concrete, which is thermal elongation with high temperatures. And I think we had some discussion when we were dealing with when we were talking about initial material behavior about thermal expansions, right? So with regard to thermal expansion also, you can see that steel and concrete are almost close to each other. So what you are seeing on the vertical axis is the thermal strain. So the coefficient of thermal elongation, alpha, you are familiar with that, right? You have used that coefficient alpha. Who has
Yes,
not,
sir.
yeah, who has
Yes,
not,
sir.
who is not familiar with that coefficient alpha? Thermal expansion coefficient. You let me know, I can explain. Okay. Fine. So, so basically that is the slope of tangential slope of this curve at any point. So if I want to know what is the thermal expansion coefficient of steel at 600 degrees centigrade, all I need to do is take the slope of this curve at this point, at that point. Okay. So that will be the thermal expansion coefficient. If I integrate all the thermal expansion coefficients with multiply with temperature, I will get these strains. So this is steel. Steel has some kind of structural change at around 750 degrees centigrade, where the thermal expansion coefficient remains constant. Otherwise, our thermal expansion is constant, thermal expansion coefficient is 0. Okay, in this zone. Otherwise, it's almost like a linear curve. Okay. Concrete also has somewhat similar range of values. Okay, so now what is the approach in the Indian code and in the international codes for designing steel structures in fire? Okay, so there is something called fire resistance rating. That is what is we design the structures for. So the idea is that first you have to calculate what is the required fire resistance, and then you have to calculate how much is available. Okay, And if not sufficient amount of fire resistance is available, then you have to do something to the member to increase that fire resistance. Okay, so one is demand side, the other one is the capacity side or availability side. So how do we calculate the demand? I am not discussing that here in this lecture. Basically, what happens is there is one code called National Building Code. You go to that National Building Code. Every country has one such code. India has this National Building Code. Are you familiar with National Building Code, NBC?
Yes, sir.
Yeah, so NBC, yeah, so if you're not familiar with, please make a note of this and go through this. I think it is available for free online. You can just download it. NBC Part 4 deals with structural fire safety. So what it does is it gives you the method to calculate what kind of fire resistance is required for a building. What is the required fire resistance rating for a building? So depending on the building height, how many stories it has, and what is the use of the building. So if you have, let's say, a building which is also used for textile factory. Okay, so maybe I have a building which is mostly offices, but on the 7th floor, somebody is using it as a storage for a lot of textile material. Then that building will be classified as a storage facility for combustible material, and then the required fire resistance will be very high. Okay, if it is a smaller building, let's say 2-story building, and I'm using it not for a big assembly or anything, it's a double-story house, then the required fire resistance rating will be low. Because why the height matters? The height matters because if it's a taller building, it will be harder for people to escape. If it's a 10-story building, it will take more time because elevators will not be working during fire. So it will take more time for people to escape that building. But if it's only 2-story building, then it's much faster. And also, what is the purpose of the building? If the building is a movie theater and it's a 7-story, 8-story building, and the movie theater could be on the 8th story, then since it's a big gathering place, again, the fire resistance rating required will be high. But if it is meant for only a small group of people, like a residential society, then you are not likely to have so many people on a particular floor at a time. So then people can escape much more quickly. So those things play a role. So based on that, you get a required fire resistance. Okay. So typically you get a single value of required fire resistance for the entire building. When you get that FRR required, you get for the entire building. That means every single column, every single beam, every single wall, every single door, whichever is supposed to work as a fire barrier, those doors, not every door. All of them have to be rated for that FRR value. Okay. So that part I am not discussing. That is basically goes into the load calculation in a way. Now I get that value. Let's say I get for a column, I get an FRR of 4. So I need to design the column in such a way so that it can last 4 hours of fire resist standard fire curve. You remember this standard fire? This yellow orange curve. So that column should sustain 4 hours of that standard fire. That's what it means. You may have requirements for half an hour, 1 hour, 1.5 hours, 2 hours, 3 hours, 4 hours. That is taken from NBC Part 4. These are the different types of fire resistance ratings that could be required. Okay. Now, the different systems have different objectives which they should satisfy to achieve this fire resistance. For example, a column. What is the purpose of a column in a building? Its purpose is to keep the above floor above it. Its purpose is not let the above floor come down. That means its purpose is to sustain or survive under the service loads for whatever number of hours you need. So if I say this building's required FRR is 4 hours, then that column, every column in that building should be able to sustain or should be able to support the service loads for 4 hours. Okay. If there is a beam, then that beam should also be able to sustain or support the loads on that floor for at least 4 hours. So whatever is the building fire resistance, that tells you the member fire resistance. I'm doing a bit of a crude translation to keep it easy. It's not really that. There are some intermediate tables also. I'm not going into those details. Basically, okay, I'll try to skip that. So basically, you get the fire resistance required for each member. Okay. Then comes the question of how do you get that? So then that's where we do this standard fire test. So this is more of a realistic fire, that black curve as we had seen. And then you have this red curve, which is our standard fire that we follow, which tries to capture a typical real fire. Okay, then basically what we do is we put that column or that beam in a furnace where we actually apply fire, and we also apply the loads that are expected on that beam. Okay, so for that the code gives you what level of loads you need to apply. You need to calculate the service load on the column, and then you need to apply those loads. And also you light the fire. You let the fire burn for the required number of hours, and the column should sustain that capacity, should sustain that fire load, and it should not start to deform too much. Fine. So that's how the testing is done, and that's how you make sure that the structure is sound, or the structure has those many hours of fire resistance. Okay. But now what's the problem with this approach? We cannot always do the test, right? For every single column, we cannot take the column to the lab and get the testing done. So there are a lot of databases available, a lot of formulae are available. What happens, let's say I have a steel beam or a steel column, and I do this test, and I needed a fire resistance of 3 hours or 4 hours. But typically steel heats up very quickly. So if the standard fire curve looks like this, temperature 0 starts from here, and as the temperature rises, at around 30 minutes, you will have 800 degrees centigrade temperature in the furnace. What is your guess? What will be the column temperature? If I take a steel column, put that in a furnace, within half an hour, the furnace reaches the temperature of 800 degrees centigrade. What will be the temperature of the column at that time? Anybody can guess? Approximately, plus minus 50.
400. 400.
Okay, let me see. 400. Who said 400?
Me, sir.
Lohit. Okay. Anybody else wants to guess? I'm talking about typical steel I section column placed inside the furnace.
It will be around 650 or something, sir.
650. Yeah, I would also lean towards 650, closer to 650 rather than 400. In the initial 5-10 minutes, you will have that kind of a gap, about 400 degrees centigrade gap. After half an hour, steel will be hitting quite to a very high temperature. In fact, after 1 hour, the furnace temperature would be approximately 950 or so, and the column temperature would be almost 900. Okay, so the column temperature closes, steel temperature I'm talking about. Steel temperature follows the fire temperature very closely. Okay, and the reason for that is because steel has
Conductor.
Thermal conductivity.
Very high, very good, very high thermal conductivity. So the entire steel cross section will be at the same temperature, and that too will be very close to the fire. Okay, in a concrete column, the situation will be very different. The outer layer will be almost at the same temperature as the fire, but that will be confined to outer 10 mm, 15 mm, something like that. The rest of the cross section will be still at a very low temperature. It will take it several hours to reach a temperature of 500, 600 degrees centigrade. Okay, that is the case with concrete. In case of steel, however, since it has a very high thermal conductivity, whatever is the temperature outside, immediately it will get translated to the inside. So initially there will be a little bit of lag. So initially the steel temperature will be rising somewhat like this, but then it will catch up quickly, and then it will be following it very closely. Okay. So in such situation, you have seen that steel at about 600 degrees centigrade, what is the residual strength? We saw the stress strain plot for steel, right? What was the strength available at 600 degrees centigrade?
0.4 or something.
0.45, 0.4, something like that, right? Correct. So about 45% strength is available, right? What is the typical service load on steel?
0.6.
Yes. So I mean, it depends. I mean, in India we take 1.5 as the factor of safety for dead load as well as the live load. So therefore, you have to do 1 divided by 1.5. So it's approximately 0.67 for columns, let's say. Correct. So under service load conditions, you would typically have 67% of the design load. But actually, what happens is that live loads are not actually present 100%. So you can reduce the live loads. We are often allowed to take 50% of the live load, not the full 100% of the live load. So if you do that, then you reach around 55%, 60%, right? And you can even be take away all the other factors of safety also, material factor of safety also, everything else, then you are at around 45 to 50%. Okay? Because there will be other design conservatism that will be built into the design provisions. So you are approximately at about 45% or 50% of the actual capacity of the column when the fire hits the structure. We just discussed and we saw that after half an hour, what will be the temperature of steel in standard fire? We discussed that. Lohit had said 400.
Yes, sir. Yes, sir.
650 we discussed.
Yeah, but it is more likely to be 650. Yeah. So at 650, so after half an hour, what will be the reduced strength? About 45%, right? And that is the service load, or that is the load that is likely to be acting on the structure at that time. So within half an hour, a typical steel structure will collapse in fire if you apply standard fire. Lohit, I'm muting you. You follow me? So typical steel structure, if you don't protect it with fire at all, against fire at all, just let it be exposed, like let the steel surfaces be exposed as they are. Paint doesn't count. If you do any paint, it doesn't offer any resistance. Okay, so paint, like paint or primer or those things don't matter. So how much resistance would you have? Typically, you would have 20 minutes to 30 minutes of fire resistance. That is inbuilt, and that is just because the fire takes some time to heat up. Okay, the structure otherwise loses capacity very quickly. Now that is of course not good enough, because minimum we need half an hour in the worst condition, but usually we need 1 hour, 1.5 hours, 2 hours, up to 4 hours of fire resistance. So then what do? We need 4 hours of fire resistance sometimes, and if I just keep a bare steel member, it may offer me about half an hour only. So what do? So there are ways which you have to learn, which are called protection techniques. So there are 3 most commonly used fire protection techniques, and out of the 3, this intumescent paint is the most popular one nowadays. It has gained more popularity in a lot of popularity in last 10 years. Before this SFRM was more popular, and before this gypsum plaster board was more popular. Okay, so how many of you have seen gypsum plaster board? You know what is gypsum plaster board? You don't know what is gypsum plaster board? You know what is gypsum?
Yes, sir.
Yes, sir.
Yeah.
Yes.
How many of you know what is plaster of Paris?
Half of CASF.
All
Yeah.
involves
Yeah, everybody should know plaster of Paris, right?
Yes, sir.
Yes, sir.
Yeah. So gypsum plasterboard is somewhat similar material. Some additives are added to that. Otherwise, it's the same material, almost plaster of Paris, basically. Okay. And gypsum is a very good fire resistant. So basically, it doesn't oxidize. It has some moisture content, but that does not play a very significant role. It just vaporizes very quickly and offers some initial fire resistance. But it is a very good thermal insulator also. So it keeps the high temperatures of fire away. And does not crumble very easily at high temperatures, even though it's a very weak material in itself. Plasterboard is not a very strong material, but under fire it does not crumble that easily. So gypsum plasterboard is also used in false ceilings. So you might often see if you go to any conference room or those kind of places, you have false ceiling, right, which is hanging. So sometimes false ceilings are made of aluminum or something, or sometimes only the beadings are made of some kind of a metal, but the panels which are placed is kind of a gypsum plasterboard. So there are various variations available. So that is one of those materials. So there are so many different applications. I cannot go into details of every one of them. So basically what happens is that you have your steel column, you have to put some kind of a clamp around it to hold on to the steel structure, and then you nail or screw these panels. These are gypsum plasterboard panels to that structure. And on top of this, you do a plaster. What do you use for plastering? Same, just gypsum plaster. So basically you take some plaster of Paris and plaster on the top, right? Plaster of Paris is used for plastering, right? That's why it's called plaster of Paris. So that is one way of protecting it. And you can, and the codes, different codes, including the NBC, National Building Code, and various IS codes, they tell you how thick the board should be or how thick the plaster should be to provide sufficient duration of fire protection. Okay. The other one, which is SFRM, one example is shown here. So basically, these are all your I sections. This was a beam with some kind of a bracket support here. Okay. And you just after you prepare the entire structure, you just go there with the machine, which spray applies this cementitious kind of a vermiculite paste. Okay, so it's kind of a vermiculite lightweight paste. It is applied. It is basically sprayed onto the structure, and it sticks. Okay, so it is slightly lightweight structure, but it can flow a little bit. They mix some air to it to give it more volume, and because if it has more volume, it has more thickness that provides more fire protection. Also, the air bubbles behave as heat insulators. Correct. So then this is applied, but the problem with both this and this. One, the plaster of Paris basically keeps the structure very, of course, you have to plaster on the top, and then it's very labor intensive. You have to attach these clamps, you have to screw these individually, you have to cut these boards in exact sizes, so you have to do the measurements. So that requires a lot of skilled labor. Okay, and then you have to plaster on again on top, which takes a lot of effort. In this case, you do this, and after doing all of this, you have to conceal everything, because in a real building, you cannot have steel members looking like this. That looks very ugly. Correct. So you have to, after doing all of this, you have to conceal it. So it is again concealed with some kind of a plaster board. Some kind of a false ceiling is required. Columns have to be, you have to put some kind of a plaster board around the column. But then the plaster board does not have to be thick, or you don't have to do any special fire protection requirement, meet any fire protection requirement. You can use any kind of material on top, because fire protection is stuck to the structural member. So that's why this was preferred, because this was less labor intensive. But now, but again, it required more work. Now, what is more commonly used is this something called intumescent paint. So when you come to IIT, all of you, those who have not come to IIT Hyderabad yet, if you go to, there is one building in IIT which is made of steel. Okay. So proper steel building. So that is called Block B, Academic Block B. So when you come to Academic Block B, you will see that the portion of the building that is made of steel, it has this intumescent paint, which comes in white color. And this is the universally available color. So it's always intumescent paint mostly comes in white color. And that is just a spray applied paint. It's simply a paint. It can be applied with a simple paint spraying machine that is used for all other kinds of paints. So there is nothing special to be done. Only thing is that how much thick layer of this paint has to be applied depends on how many hours of fire resistance you need. And that catalog will be given by the paint supplier himself. So if he will tell you, if this is the cross-section size that you have and you need 3 hours of fire resistance, then you have to apply at least 3 millimeters of paint. So then you need to coat several coats. Maybe one coat can be approximately 0.7 millimeter, let's say. Okay, 0.7 millimeter of paint you can apply in a single coat, and you want to go 3 millimeters, then you do approximately 4 coats or 5 coats, between 4 or 5 some coats you can do to meet your requirement. Okay. The way intumescent paint works is very interesting. So when I was a kid, I don't know what kind of firecrackers you guys used to play with. When I was a kid, we used to have this small tablet, sort of a black color tablet used to come on Diwali. You light that tablet, and then it starts to expand and used to curl around that. So basically, you have used that one, you have played with that. So the tablet is only this long. Yeah, there is background noise. So the tablet is only this big. The tablet is only this big, but when it burns, it creates this char. Char means like ash kind of a thing, which has some structure. It does not collapse immediately. So it maintains its integrity for a while, and it keeps coming out of the tablet and curls around and forms a snake kind of a thing. So this thing also has similar kind of characteristic. So as it is heated, this material, white color material, it starts to char, and as it chars, it expands in volume. Okay, and it maintains its structural integrity to some extent, so that it does not immediately collapse or it does not immediately fall down or fall. It remains stuck to the structure, but it expands several times. So a 3 millimeter thick layer, once heated, can expand up to almost like 30 millimeter or 40 millimeter. So then whatever thickness requirement you had here, it also provides the similar kind of a thickness, but that is only when it is heated. When it is not heated, there at that time it is only 3 millimeter thick and gives you a very smooth, clean surface. So this one is aesthetically very pleasing, and it can be used, and you don't have to really hide it unless the architect wants it. sometimes architects just like to have these structural members exposed. So this is very nice because you can see all the structural shapes. Okay. So here you can see also very closely when they had a beam here, and then they had a cold form steel section, a cold form steel sheet on top of this one, right? So above the steel beam, you had a cold form steel sheet on which the concrete was cast on this slab. The slab was cast on top of it. So when they spray applied this one, they spill over a little bit, and that is shown on the cold form steel, which is not a very good quality workmanship, but probably they just decided to leave it like that. Okay, fine. So you understood how it behaves, right? So intumescent paint is the more commonly type of fire protection technique that is used these days. How much time I have? 25 minutes almost. Okay. So how do we calculate how much fire protection to apply? There is NBC Part 4. There is AISC Design Guide 19. So AISC 360 is the American Steel Design Code, but also AISC has several design guides. So AISC 360 is available for free for anybody to download, the latest version even. But these design guides are not available for free. You have to pay for them. So Design Guide 19 is the one that is used for fire resistant design. Similarly, there is another one, Design Guide 21, I think, if I'm not mistaken, that is for earthquake resistant design. Likewise, they have a lot of these design guides where they do some solved examples, etc. Okay, so these design guides are not the law. AISC 360, that is the design guide, that is the design specs, that is the law. That's what you have to follow. These design guides are typically for your aid. Okay. So you can use the provisions given in these tables and other specialized literature to design the fire protection. So one such table I'm showing here, that is for encased steel column. Okay, so that is a steel column, but you are encasing it with some kind of a gypsum plaster board. So if you are using a plaster board with 1.6 millimeter wire binding at 100 mm pitch, so that is only the wire binding property. So you have to use some kind of a wire to wrap it around, to wrap around the board to hold it in place at 100 mm pitch. Finished with lightweight aggregate gypsum plaster. So that is again, some lightweight aggregate is used with gypsum plaster, that is plaster of Paris. So when you plaster with plaster of Paris, you don't simply use plaster of Paris, you also use some aggregate to give it a better, higher strength. Not less than the thickness is specified. So if my plaster board, for example, is 9.5 millimeter thick, almost 10 mm thick plaster board, then for 1 hour of fire resistance, I require 10 millimeter of plaster on top. Okay. If I need 1.5 hours, then I need 15 mm plaster on top. If I need 2 hours of fire resistance, then I cannot achieve that with 9.5 millimeter plaster board. I have to go with 19 mm plaster board. And on top of that, I have to apply 10 millimeter additional plaster. Okay, so see the difference between plaster board and gypsum plaster. On top of the plaster board, you have to apply the plaster. So total thickness will be 19 plus 10, 29. Likewise, here the total thickness will be 19.5. Here the total thickness for 1.5 hours, 15, that is 24.5. Okay, this is 29. And likewise, the thickness increases as you want to achieve higher and higher fire resistance. Okay. So 20 mm thick plaster is really, really very thick plaster. I don't know how easy it will be for the plasters to stay. You need really good workers to hold that plaster in place. Similarly, if you have a beam, okay, so also the beam size matters. So this much of fire protection is required for this beam or a bigger beam. If your beam size is smaller, then do you need more protection or less protection? If your web and flanges are thinner, if the beam size is smaller, that means your flanges and webs will be thinner.
More protection.
More
protection. Very good. So if your sections are thinner, they will heat up faster. So then you need more protection to avoid that fast heating. Okay. So this table works for this section or bigger sections. Okay. Not for smaller sections. Likewise, there are tables available for a few sections in between. So then you can use the entire spectrum. Again, here it gives you requirements up to 3 hours of fire resistance. You cannot achieve 4 hours of fire resistance with these kind of methods. Plus, mostly for beams, you don't need that because at a time, a beam protects or a beam provides support for only one floor. So you don't really need 4 hours of fire resistance rating for a beam, but for columns, you do. That is as per the requirements in NBC Part 4. Okay, so likewise, it gives you what is the what is the plaster board thickness and what is the plaster thickness that you need for different fire resistance ratings. Okay. Also, there are other ways of designing. So in this one, okay, let me just take a step back. So what is the code telling you? What is the entire process for fire resistance designing? Can anybody quickly summarize? If I have a building and I want to know how to design, how to make sure that my structure is fire safe, what will be the process? If you have followed whatever I've been talking about. The process is so simple. Because I have talked about a lot of things which are not necessarily involved in the typical design process. So you might be confused a little bit. Let me see if anybody has been able to follow the basic steps. Basic steps are very simple. Lohit, yeah, you want to try? Lohit, there is a lot of background noise. As soon as you start talking, there's no other noise. There's something wrong with your microphone or something. You try to remove your microphone and talk directly to the laptop. Anybody else wants to give it a try? No?
So now the voice is clear? I mean, is
Yeah,
there
no,
any noise?
Yeah, no, the noise has gone away now.
Yes, sir. Sir, I mean, first we need to see whether the building is made of steel or not. If it is steel, then if any fire protection is not there, then based upon the importance, I mean, whether it is the what kind of building it is, whether it is a movie theater or height of the building. So based upon all those things, first we'll rate the building of what kind of fire rating we need it, whether it is half an hour or 1 hour or 2 hours. So depending upon the fire rating, then we'll go for the fire protection measures, whether we need to use the intumescent paints or other gypsum plaster boards. So based upon the fire rating, we will simply do the protection measures. So
Very good. Yes. So yes, exactly. That's what is required. So basically, just to reiterate, first you look at the building, whether how tall the building is and what is the use of the building. With these two pieces of information, you decide what type of fire protection is required or what type of fire resistance is required. That is called fire resistance rating. Those tables are all given in NBC part 4. NBC part 4, yes. So there you will get that columns have to be protected for 4 hours, beams have to be protected for 3 hours. You will get those numbers very quickly. It will just take you like 5 minutes to get to that. Okay, so once you get the required fire resistance rating, then you simply come to tables like these, the one that I have shown here. So, okay, this is my beam. This looks like a steel beam. That's what I'm using here. For concrete, there are separate tables available. I'm not going to get into that. So the required resistance will be same for whether it is steel or concrete. Then comes the question of whether the steel or whether the beam can provide that much of fire resistance. For that, there are separate tables. For concrete separate, steel separate. For steel, since they cannot on their own provide much of a fire resistance, so you have to, let's say I decide to go with plaster board, gypsum plaster board. I'll come to this table and pick the thickness of the plaster board and thickness of the additional plaster required to achieve that fire resistance. That's all. Okay, that is the entire design process. In that entire design process, seems so simple, but did we consider any loads here? I just looked at whether it's a beam and whether it's a column, and then designed the beam or the column based on whether it's just simply based on whether it's a beam or a column, or whether what kind of structure it is a part of. I never considered any loads on the beam. I never considered any kind of boundary conditions of the beam. Correct? So typically, I mean, we are all structural engineers. We itch for those information, right? We cannot. I mean, it seems so absurd that we never considered the loads acting on the beam, and we designed the fire safety of the beam. Okay, so the reason for that is that fire safety has not been at the center stage of the entire structural designing process. Generally, it is done as an afterthought. Okay, the fire accidents are not as common as, say, failures under gravity loads or failures under live loads and things like that, and that's why generally they get ignored. But as the times are changing and we are more cautious about safety of people, safety of structures, the costs involved with the catastrophic failure, now the focus is shifting more towards a more proper, more scientific approach rather than this kind of a very crude approach wherein We simply just go by whether it's a beam. If it's a beam, if it's part of a 10-story building, you need 4 hours of resistance for columns, you need 3 hours of resistance for a beam. So for a beam, you simply go slap a 19 mm plaster with 20 mm plaster board with 20 mm plaster. That's all. As simple as that. But that approach is flawed. There are a lot of issues with this kind of an approach. There are issues of what kind of standard fire you have used to develop these curves, but those are more nuanced. There are, even at a fundamental level, there are many issues. Like we never considered the load acting on the beam. Maybe this particular beam was carrying a load which was way, way smaller than the service load. You assumed a particular service load to come up with these values, but that service load may not actually be present on the beam. So then do we really have to apply this kind of a thing? How about other ways of load transfer of the beam? Right? Because when the beam was tested in a furnace, it didn't have any mechanism possible wherein it could have transferred the load to other neighboring beams. But maybe in real life, it can transfer those loads to the other beams when it deforms. And maybe then we don't need all this fire protection. Or maybe we need more fire protection for certain cases. So all those possibilities are completely disregarded, are completely ignored. Okay. And now intumescent paint coating is quite expensive, and that adds a lot to the cost of a structure. And therefore, people want to be more economical and more scientific in their approach. And that's where this research is headed these days. So the Indian codes are also keeping up with the international codes, and all the structural codes are also starting to accommodate some provisions for fire safety. So for steel, for example, we only had this NBC Part 4, which used to tell us what kind of fire protection is required, right? And IS 800 before 2007 version was completely silent on fire safety. It had no discussion on fire safety at all. Now in 2007 version, they have added a chapter on fire safety. Let me take you to that chapter quickly. Have you guys seen that chapter on fire safety?
So there is a section 16, sir, I guess.
Yes. Yes. So this section 16 here talks about fire resistance of steel structures. So this is a new edition that was done in 2007, and in the next version probably they will improve it further. Okay. So here they talk about fire resistance. How do you achieve a particular fire resistance? They talk about critical temperature. They talk about limiting steel temperature, but that is the maximum temperature you can you can allow, and so on. Okay. So basically in this provision, they are basically heading to that, in that direction, where you have to consider the loads acting on the column or on a beam, and then calculate the resistance of the beam or column at that time. So the provision that is available in the Indian code is this. So what it says is that, let's say I want to have a column designed for 1 hour of fire resistance. Okay. And now for 1 hour of fire resistance, I provide some kind of a fire protection around it. I want to check whether that fire protection is sufficient or not. So you can do a lab test, you can do some analysis or something, try to figure out what will be the temperature inside the column at that time. Now, what you do is, once you know the temperature, let's say after 1 hour, I find out that the temperature in column will be 600 degrees centigrade, assuming that it will be uniform throughout the column. That is not guaranteed, but assuming that the heating is from all sides, and that is the maximum temperature that you can have, let's say 600 degrees centigrade. Then this table says is that for 600 degrees centigrade, you come to this curve and calculate the first one is basically your yield stress ratio. So at 600 degrees centigrade, your available yield stress will be approximately 0.42 of the original yield stress. So about 42% of the yield strength will be available, and approximately 50% of the elastic modulus will be available. The other curve, the smooth curve, that is your modulus of elasticity. So about 50% of your elastic modulus will be available. So you calculate the new elastic modulus at 600 degrees centigrade and the new yield stress at 600 degrees centigrade. And then you use the existing column and beam design equations, whatever are available in the earlier chapters. So section 7 deals with columns, right? Is that 6 or 7?
7 compression.
Compression members. 7, right? Yeah. So section 7 has these equations. These equations you have seen already, right? So you just use the same equations. Only thing that you need to do is that lambda, instead of lambda, you use lambda bar, you use lambda theta. Okay, wherein you substitute for the respective k value, respective E values. Likewise, you use Fy, a new Fy, which corresponds to, or instead of original Fy, you use Ky theta multiplied by Fy, which is Ky theta taken from this table. Okay. So likewise, you change the equations, which is only just to account for the temperature effect on the elastic modulus and the temperature effect on the yield stress, and get a revised capacity, which will be reduced capacity for 600 degrees centigrade temperature. And then from the analysis, you would know what are the service loads. So you can take dead load plus live load, you can take dead load plus half live load, whatever the design philosophy the code follows. The Indian code follows dead load plus live load. So you take that much of service load, and at 600, this is the reduced capacity, and then do a comparison. Okay, so now this is a more similar thing you can do for the beam also. So this is a more scientific way or more accurate way of designing for fire, and that has already been incorporated in IS 800. It has not been incorporated in NBC yet. In NBC, still those original provisions are applicable. So you can either go with this approach or you can go with NBC approach. It's your choice. The challenge with this approach is, how do I calculate this temperature 600 after 1 hour? So I just said that after 1 hour, let's say the temperature is 600 in steel, but how do I know that? There are a lot of other databases are available. So for example, if you had applied intumescent paint, then the supplier of the intumescent paint will tell you that if this is your steel section, after 1 hour of standard fire, temperatures will be this much in steel, if you apply our intumescent paint of these many millimeter thickness. Okay, or let's say he would say, if you need a temperature to be 700 or below, you don't want the temperatures, or 500 or below, you don't want your temperatures to exceed 500, then you have to apply at least these many millimeters of, or at least these many coats of my intumescent paint. So such kind of catalogs are available. You can use those, but those catalogs are also not guaranteed necessarily in India. They are mostly certified by international agencies. Generally, that is acceptable in India. Okay, you followed it? Similar kind of equations are available in the US. This is America. So for India, I showed you there were only two curves available, Fy and E with temperature. As the temperature rises, the steel's E value decreases. This is Fy value decreasing, and this is E value decreasing. In the US, they follow this trend, where in the Fy value decreases like this, the E value decreases like this, and the proportionality limit decreases like this. Okay. And then you take the E value and Fy value from these plots, plug into the equations, and get the column capacity. Similar equations are available for beams. Similar kind of things are available in the Eurocode also. The material properties are similar between Eurocode and American code. In Indian code, it is different, but equations between the American and European codes are different. The member design equations. Anyway, so those things you can always learn. You can go to the respective code and find out what is mentioned there, what is given there. So if we compare, let's say, column strength at high temperatures. Okay, so what I've done is I've taken 600 degrees centigrade temperature. For different slenderness values, what does the Indian code say? Let's say I have taken class A curve for the Indian code. So this is what the Indian curve looks like. Okay, for a column design for different slenderness values. So KL by R is varying from 0 all the way to almost 170. So at 600 degrees centigrade, column curve looks like this. But the European, this is green one, and the American, the red one, they look like this. So what do you get from here? What is the observation?
American and European are much conservative than the Indian code.
Yes. So personally, I have seen how the European code and American code have these equations have been developed in the US and America, in the US and Europe. I've gone through the papers which had proposed these equations, and then so I have followed this development very closely. So I know how these equations came into being, and they are verified against some experimental work, experiments that were conducted in those countries, or some analyses that were conducted in those countries. The European curve is directly taken from, compared with some experimental data. This American one, they had used some experiments to validate their analysis. Then they had done a lot of analysis to compare the results or develop the equation. The Indian code, I don't know exactly where they came up, how they came up with this curve. So usually what happens is that in the Indian code, we put these equations, we don't give any references. So it is very difficult for us to follow where these equations have been taken from. So I don't know exactly what is the scientific validity, and that leaves a bit of a doubt. I'm sure the scientific committee or the Codal committee must have taken various considerations into, or various research that is available into consideration. But at least this curve clearly shows that the approach, if you take the Indian approach, you are likely to be unconservative, because these, I know, are developed based on some real experiments as well as analysis. And there is quite a bit of unconservatism in the Indian code. At least, I mean, if you look at intermediate slenderness values, you are almost predicting twice as much capacity. Right? Make sense? All right. So here is an example based on the American code. Similar thing you can do with the Indian code also. I have not done that here. I'll skip this part. These are some parts from my research also. So I will skip that. The time now is almost fine. Okay, this I don't have to discuss. Okay, so in the next class, this is an interesting topic. This basically should enthuse you a little bit about fire research, structural fire research. So far, whatever we have discussed is the current state of practice. Now we will talk about kind of state of art. So I'll show you a few examples of real buildings and how they behave in fire, and what actually happens and how it becomes very, very complex soon, right? So in the next class, we will talk about this, and if we have time, we will continue with the base plate discussion. Otherwise, we will extend that to the next week. Okay, we have a class this Thursday, right? Yeah, yeah.
Yes.
All right. Any questions, class? All right. So we can call it a day.